One of my favorite questions is to ask you to decide on the relationship between two molecules. Are they enantiomers, diastereomers? Are they constitutional isomers? Are they the same molecule? Or are they completely different molecules? So let's look at a couple examples of those. So here are a pair of molecules, and we're asked that same question to decide the relationship between them. First thing I like to do is make sure that the connectivity is the same. Right? Do I have the same, in this case, 7-carbon chain with the same substituents on it? If I don't, then automatically they're either constitutional isomers or they're different. So in this case, we have 7 carbons across. We have an ethyl, a methyl, and an OH group. And we have that same 7 carbons in a chain here, except we sort of have we start from the up position and then go across. So you see that the methyl and the OH have been swapped in their locations. It's still 7 carbons, still has an ethyl, still a methyl, and still an OH group. So I wouldn't say they are not constitutional isomers, they're connected the same. And it looks like they have the same formula, so they're not different molecules. So that narrows it down to enantiomers, diastereomers, or identical. Then I take a look at, make sure that the substituents are in the same spot, and they are, so they're not constitutional isomers. So we're looking at, we're then looking at the stereo centers. If we look at what appears to be the rightmost stereo center, it appears to be flipped, but if you notice there are 2 ethyl groups attached to this carbon and 2 ethyl groups attached to this carbon, so it's not a stereo center. So let's not get mixed up by looking at these 2 carbons as stereocenters and being flipped. They're not stereocenters, they're just there. They have 2 ethyl groups on them. The next stereocenter would be this methyl group that's got a wedge here and a dash here, so certainly that stereocenter has been inverted, leading us to the idea that perhaps we have enantiomers or diastereomers. We can't have identical molecules anymore because we have at least one inverted stereocenter. The last stereocenter is this one, OH, methyl, hydrogen, and the rest of the molecule. This one has also the OH, the methyl, the hydrogen, and the rest of the molecule. However, it's a little difficult to decide what's happened to this stereocenter because 2 of the groups have been switched. So we could observe that there's a wedge, and that we've flipped 2 groups. And if we remember from reading, flipping 2 groups will automatically invert the stereocenter, so the stereochemistry. So if I underline this one here as being inverted, and we remember that flipping 2 groups also will invert the stereochemistry, I have inverted both stereocenters on these molecules as I've gone from left to right, and thus they are then enantiomers. If we didn't remember that flipping the stereochemistry, or flipping 2 groups inverts the stereochemistry, we could have assigned R and S configuration to these 2 carbons and figured out, are they the same, both R or both S, or are they flipped? So let's do that quickly right here. The highest priority is the OH, and then the rest of the molecule gets the second priority. Third priority is the methyl, and then the hydrogen that's going back. So I go this way. This is an this is an R stereocenter. And if we do the same thing over here, highest priority is the OH, the rest of the molecule is 2, the methyl is 3. We have now a counterclockwise, and so this is S, and so we've gone from R to S. Again, we've inverted the stereochemistry. We've also inverted the stereochemistry at these other remaining stereocenter. So again, we have a set of enantiomers. Let's look at this possible type of question. Here we have 2 different drawings, and that might make it a little more confusing at first if we don't think about it properly. So again, here's a Newman projection, and here is a more or less skeletal line structure. And the first thing I like to do is make sure I have the same connectivity. So I have a carbon in the front, and I have a carbon in the front, and I have OH, H, and methyl on that carbon. I have the same 3 substituents on this carbon. So at first part of my glance, it looks like we've got the same connectivity and the same formula. Then on the back carbon, which is remember that's the circle here, that's also this carbon, I have H, chlorine, and ethyl. Here I have H is invisible here, I have the chlorine, and I have ethyl. So they do have the same connectivity, they have the same formula, so they're not different molecules. The next question is, do I have any stereocenters? Yes, I have 2 stereocenters. How are they related as we go from the left drawing to the right drawing? And in this case, it might be easiest to draw this molecule as a skeletal line structure and then translate it from there. So let's go ahead and do that. I'm going to have a line, and I'm going to be viewing it this way. And so right here is the front carbon, and I'm going to just put a little circle there so we remember that that's the back carbon. And going up from this line is the hydrogen. Going back into the screen is the OH. And coming towards us now, as we draw this in the plane of the screen, is the methyl. And if we look at the back carbon, we have the ethyl going down in the plane of the screen. We have the chlorine coming out towards us, the same direction the methyl is. And then we have the H, which we don't normally draw, but we'll put it in here, going back. And now hopefully you can recognize again that all 3 groups on both carbons are the same. And the easiest thing here might be could do a couple things. I'm going to redraw this, rotating around this carbon-carbon bond as necessary to put the ethyl in the same plane as the ethyl up here, so in the plane of the screen, but I want to point it upwards. And I want to put the methyl in the plane, but I want to put that upwards as well. So let's redraw. So the ethyl goes up, and that means the hydrogen swings around 180 degrees and becomes a wedge downwards, and the chlorine swings around 180 degrees and becomes the dash. Remember, we're essentially rotating the right carbon 180 degrees. And then we're going to rotate this carbon so that the methyl rotates up into the hydrogen location. So I can basically just take these 3 groups and move them 1/3 rotation like this, keeping the wedges and dashes in the same spot, but now they have different substituents on them. I'm just going to rotate those substituents. All right, so now let's compare what we have. This carbon here looks very suspiciously like this carbon. I hope you'll agree that these have the same 3-dimensional configuration. OH coming towards us, methyl in the plane of the screen. This carbon, though, is flipped, right? The chlorine is a wedge on top, it's a dash on the bottom. And so I have inverted the stereochemistry on one of the carbons, but I've retained stereochemistry on the other. And that, by definition, is a diastereomer. So these are diastereomers. And we established that by redrawing our Newman projection and comparing it to the right side drawing. Now, if you're really practiced, you can probably come up with R and S configurations of this carbon and this carbon as it's drawn here on the page. As I said, that takes a little bit of practice. You need to be able to rotate this molecule in space inside your mind, or you could redraw it. And so I think that's also a fine technique. I'm not going to demo that here. But in this case, we find that the front carbon has the identical stereochemistry, and the back carbon has been flipped. It's been inverted. And if you want to establish R and S for that, that's fine. But because there's only 2 stereocenters here, it's very easy just to pick out that this stereocenter here is identical, and this one is inverted.